Hello! In the previous lecture we played an interesting game. Somebody gave us a differential equation. Now, of course, the first thing that we do, we check on restrictions. So here is the plane, x and y, where the solutions live, hopefully. And then we look at the right-hand side, essentially, and we say, okay, there may be a region which is forbidden. We cannot go there. Okay. Let's say there's also another restriction in the form of a curve. So this curve is forbidden. Definitely cannot go there. And then we look at the remaining part of the plane. We look at the right-hand side. We play with it a little bit. And we say, okay, this region splits into more subregions. And in each subregion, we know something about monotonicity of solutions. If the solutions go through here, they are increasing. And over here, they are decreasing, and so on. It was a very nice game. I hope you enjoyed it. But we actually avoided a key question. Let me go back to the conclusions that we had. Let's say this one. Okay, over here in this region, when solutions pass there, they are increasing. That's nice, but how do we know that there actually are any solutions passing through that region? And the honest answer is, we actually don't know. Because even a very nice differential equation, a simple one, may be really bad. There are differential equations, and they are not crazy, they are not weird, that do not have any solution at all, not even a tiny one. So then a conclusion like that is pretty much useless. So that's actually a typical basic question in mathematics. When we study some type of a equation, it need not be differential, any type of equation, we look at it, and one of the key questions is, okay, this type of equations, do they have solutions or not? Very good question. Now, we already saw an existence theorem for differential equations. When we are looking at separation, there was a theorem and it said, okay, if those components on the right-hand side, which are separated, if they are continuous, then we have solution. This can be actually generalized. So let me show you the first important result of today's talk. Okay, here we go. This is called Peano's theorem on existence. That sounds good. And let's have a look at it. So we have our differential equation of the general form, first order explicit differential equation. And now they talk about intervals, and we should imagine them along the x and y axis. So interval I could be somewhere here, and interval j could be somewhere here. And then when you form the cross product, it creates a rectangle. So we are in fact talking about rectangles in the plane. That's a rectangle, okay? And the theorem says, if we can find an open rectangle on which the right-hand side as a function of two variables is continuous, then for every point of this rectangle, here we go, there exists a solution passing through it, but it only exists on some neighborhood of x0, which is the x-coordinate. Here is x0, here is y0, and through this point there passes a solution which is guaranteed to exist on some neighborhood, and we don't know how large. So the good news is we get existence with a fairly mild assumption, continuity. Continuity is quite weak. On the other hand, there are several things that we do not see in this theorem, and that's equally important. So first of all, it does not say that this solution would be, let's say, large or long. When you imagine x to be the time, then we would like our solutions to last for a while. I would like to see a solution like that. But unfortunately, the Peano theorem does not guarantee that. It does not even guarantee that the solution would run across the whole interval I. And the reason is that, well, there are some differential equations which are not really well behaved. So we cannot say more. There is another important thing which it does not say. In the name of the theorem, there is the word existence, but not the word uniqueness. It can easily happen that you take a point, and there are actually two solutions passing through that. Or it can happen that two solutions are merging into one. Or perhaps another solution is splitting, like that. And these things are not really welcome in applications. Like when you throw a stone or a chalk, it would be really unpleasant if this chalk was flying and suddenly said, okay, wait a minute, do I feel like going this way or that way? We do not expect things like that in applications. So in applications, uniqueness is usually very important, and the Peano theorem is not strong enough to guarantee uniqueness. But still, it's a good starting point. So let's try an example. It will be the familiar one. Y prime is equal to 2x times y minus 1. Okay, let's have a look at it. We start by drawing the plane, x and y. That's our playground. How about restrictions? Well, no restrictions. So the solutions do exist, perhaps, on r squared. That's the potential. Perhaps they are there. Okay, we are supposed to identify some rectangle on which the right-hand side would be continuous. Well, that's a polynomial. Polynomial in two variables. It's continuous everywhere. Okay, let's be tough. This is continuous, this f, on r cross r, and therefore by Peano theorem we have existence, local existence, on r square, which is wonderful. So everywhere in the plane, no matter where you put your point, there will be some tiny solution passing through it, or perhaps large one, lasting for a long time. We don't know. But everywhere there are local solutions. So now it makes sense to talk about in this region these solutions are increasing and so on. Yeah, that's very nice. Good news. Okay. But as I said, we are not quite happy because this uniqueness problem is really bothering us a lot. So can we somehow add perhaps some assumptions, be a little bit more strict, and as a reward obtain uniqueness? That would be very nice, and there is such a thing, but before we get to there, we have to introduce a new notion. Perhaps let me start by recalling something from the previous lecture. When I look at this differential equation and I look at this picture, I can see interplay of actually 2 points of view. On the left, I can see derivative of a function, so I can see the plane as dependent and independent variable. X is independent, y is dependent. But on the right-hand side, I can see a function of two variables. It treats x and y equally, and it has some behavior. I can sketch a graph of a two-dimensional function, things like that. Now, this differential equation actually represents a feedback. And in applications, you can even imagine that there is no x in it, so it's a fairly simple feedback. It tells us the situation as it is, and perhaps the time, influence how the situation changes, because y is some quantity that we are interested in. So it's a feedback equation. Every explicit differential equation, meaning every differential equation which has isolated derivative on the side, is actually an equation about feedback. You look at a situation, and you learn how the situation wants to change at that moment. And the Peano theorem says, if this feedback is continuous, then the system behaves reasonably, which means at least there are some local solutions. What does it mean reasonably? Continuity. Well, it means that if you change the situation a little bit, then the feedback does not change sharply. There is not a jump in the feedback. Okay? So that's a fairly gradual change. Nice. Now, if we want more, if we want uniqueness, we have to ask more of this feedback. We want this equation, which is describing the feedback, to be reasonable. We want the feedback to be, let's say, proportional to the changes in the situation. That's a good way to put it. Okay? If you change the situation a little bit, and the situation now, let's focus on y, because that's the quantity. If your quantity changes a little bit, then the corresponding feedback should not change totally out of place. Now we know that we don't want jumps, but we also do not want big changes. Now, let's focus on a function of one variable. Let's have a look at it here. And I'm going to use y. How do you describe mathematically that the change in the function, in the feedback, is not out of proportion with the change in the variable? Like that. You look at the function at two different instances, so it's y1 and y2, and you ask about a change, compare it with the change in the variable. So that's an inequality which puts proportion between the change in the variable and the change in the function. Now this k, it should be a constant. And this constant, of course, should be universal with respect to something. So we have to say where we take y1 and y2. So y1 and y2 are taken from a specific interval. Let me call it j because it's on the y-axis. Okay? This is how it works for a function of one variable. If a function does exactly this, then it's called Lipschitz. Or sometimes people say k-Lipschitz. It depends whether you really care about the constant k or not. Sometimes you are just happy to know that there is such a constant. And then you can just say, I have a Lipschitz function. But if you care about the number, then you put it into the name. Okay? Very simple. Now, how do we imagine Lipschitz functions? Let's rearrange it a little bit. I can write it like that. Phi y1 minus phi y2 divided by y1 minus y2. And then, properly, I should be putting absolute values on the top and on the bottom, just by dividing, but then I can pull it out. And I get this. Okay? That's an equivalent description if I put here y1 not equal to y2. Now it's equivalent. And this tells me actually something about a Lipschitz function. We do know an interpretation for this fraction. We know it from calculus 1. We saw it there. You look at the graph and you connect 2 points on the graph, and this is actually the slope of the connecting line, of the secant line. So a Lipschitz function is a function where if you start looking at different places on the graph at secants, they are not growing too steeply. There is a bound on the steepness of the secant lines. So let's have a look at some Lipschitz functions. For instance, the function sine. It's Lipschitz on the whole real line. No problem there. Because when you start connecting points, 2 points, you take pairs, anywhere on the graph, you will never get slope which is larger than this or this. One in absolute value, because we know, well, we will get to it. But we know something about derivative, and we start having the feeling that it has something to do with it. Okay, so sine function, definitely Lipschitz. How about e to x? That's a good question, because e to x, as we know, it bends upwards, it's concave up, and therefore when you are putting the connecting lines, you can imagine that they can be as large as possible. So the exponential function is definitely not Lipschitz if I look at it on the whole real line, but it is Lipschitz on any interval of the form negative infinity k. Or you can close it if you want. It doesn't really matter whether j is open or closed. Okay? Actually, typically, people take it closed in applications. So let me put this as an alternative. Okay? So exponential is Lipschitz on bounded intervals. The same goes for x squared, things like that. Lots of functions are Lipschitz on bounded intervals. So there are many Lipschitz functions. You just have to make sure that the slopes do not run away on you. So let me show you something here. Square root of x, it looks like this. Now we have to draw it properly. The function square root of x is hugging the y-axis at the origin. So it goes like this. That's the square root of x function. And because it is hugging the y-axis, the slopes are actually tending to infinity. So this one is not Lipschitz on any interval of the form 0, let's say k. There is a problem at 0. Infinite derivative, improper derivative if you want. So now we have a fairly good idea of the notion of a Lipschitz function. These are functions that do not have steep growth or falls. How do we recognize them? That's a good question. because, of course, we are not expecting to be so lucky that the right-hand sides of our differential equations would be just simple sine, exponential, and so on. Well, there is actually a test. When you recall from Calculus 1 this expression, there was a theorem which had it as a very prominent conclusion. The conclusion was, if you are interested in such a slope, you can find it in the form of a derivative. So the mean value theorem says that this ratio can be replaced with the derivative at a specific point. We do not know which one, but there is such a point. That's the key for the mean value theorem. We can turn it around. If all the derivatives on some region that we are interested in are bounded by some constant, then consequently also all these ratios should be bounded. So when we are talking about Lipschitz functions, probably the easiest way to recognize them is to look at the derivative of your function and see whether it's bounded or not on the region that you want to have. So you look at the derivative of exponential, of sine, derivative of the square root, and you see whether you have boundedness. You do or you don't. And this tells you a lot about the Lipschitz property. I think we are ready. Let's have a look at it. So this is the second and the last theorem, because you cannot get more than existence and uniqueness. This is the best you can get. Let's see. We have a differential equation of the familiar form. We have this rectangle, I cross j, and we have a function which is continuous on this interval, which is nice. So that's actually the Peano situation, continuity. But now we also want this function f, the right-hand side of our equation, to be Lipschitz as a function of y. So we fix x, and at that moment it becomes just a function of y, like we have it here, and we want this to have the Lipschitz property. Now the trick is, you have this rectangle, and for this rectangle you have different axes. And you are moving up and down with the y variable, and you see, okay, I have Lipschitz property here, and I have it here, and I have it here. But all these Lipschitz properties, they could have different k's, which could be unpleasant. So the theorem is stated in a more careful way. It says, there is a universal constant k, and this universal constant k works for all those Lipschitz tests for every x. Okay? So there is universal k, and when you are moving all over this rectangle in the y direction, it doesn't matter where you move, this 1k always serves as the k Lipschitz constant. Okay. And it says, if you have this, then through every point there is a solution, local solution, and moreover, it's unique. So now we know that these three cases, the join, the split, the cross, they are not allowed if the right-hand side is Lipschitz, which means if the feedback is gradual, which happens a lot with differential equations. So this is a very strong theorem. By the way, some authors do not just put Picard there, but also other names. For instance, Picard-Lundelöf is quite popular. I have even seen a version with 3 names. So there is a little bit of confusion, but the Picard name is always there. So when you say Picard theorem in uniqueness, everybody will know you mean this one. By the way, it's not the Picard from the Star Trek. It's a different Picard. Okay, let's go back to business. Okay, let's identify Lipschitz property, the rectangles on which the Lipschitz property would work. I look at it and I say, okay, how can I recognize the Lipschitz function, the Lipschitz property? I don't quite see it. It's a polynomial with 2 variables. Okay, let's move to this. Instead of asking for Lipschitz function, for Lipschitz property in general, we will ask for boundedness of the derivative. Now we are using y as a variable, and that's why you have to take derivative with respect to y. Let me state it as a corollary. So this is a practical version, so to speak, of the Picard theorem. I actually copy-pasted the Picard theorem, but instead of talking about Lipschitz functions, I talk about the boundedness of the partial derivative of f by y. This is not actually an equivalent statement, because you may have a Lipschitz function which does not have a derivative. That's why it goes in only one direction, this direction. You know about derivative, you know about function. That's the direction that we are interested in. We are lucky, okay? So if the partial derivative by y exists and is bounded on my rectangle, then we have existence and uniqueness. We are lucky. Okay, let's have a look at it. So, partial derivative. My f xy is 2x y minus 1. And the partial derivative by y, okay, x is a constant. This is just a polynomial of degree 1. The partial derivative is 2x. And now I can ask, where is it bounded? On what kind of rectangles is it bounded when I'm looking at my basic plane? Well, we have to start with a new picture. Okay. Is the function 2x bounded on the whole R square set? The answer is no, because if we go to the right and x increases to infinity, then also 2x goes to infinity, and therefore it's not bounded. So at this moment, it's actually good to ask the opposite question. Can I make this expression to blow up? And the answer is yes, if I send x to infinity. So that's exactly what I want to prevent. I want to restrict my attention only to points whose x-coordinate is not extremely large. So I cut them away. Here we go. I choose some constant m. And I say, okay, the points which are more to the right, they are forbidden. As long as I stay to the left, then the x-coordinate of those points is not extremely large. It's not close to infinity. But of course, minus infinity, another trouble. So I have to cut away also minus infinity for the x variable. I could put another name here, another letter, but it actually does not really make much difference. You will see why, if it's symmetric. So I'm going to introduce minus m as this location. So it's a nice symmetric strip, which extends upwards and downwards without any restriction. It's an infinite strip. And I claim that this is my rectangle. So the I interval goes from negative m to m, and the j interval goes, well, it's actually the whole real line. So my statement is, on interval minus mm cross r, the partial derivative is bounded. How do I know? Well, let me do a little sidestep. If a point xy belongs to this set, then definitely x in absolute value is at most m. And therefore, the partial derivative by y is bounded by, okay, 2 here, x here, 2m. And this would be my k. Okay? And this k does not depend on y, does not depend on x. It's a universal constant which yields Lipschitz property. So it all fits together. So this is a good rectangle. It's a rectangle on which my partial derivative is bounded. And therefore, by Picard, I have local existence and uniqueness. So that's the conclusion of the Picard theorem. I identified a specific type of rectangle, and on this rectangle, everything is really nice. However, this is just the first stage. Before we get to the second stage, let me make a little side trip. As I said, we are really interested in applications, in solutions that last for a long while. So what's happening here, I have this strip, and I have a local existence of solution. There is actually a stronger version of the Picard theorem, and it says, through every point of my rectangle, there goes a unique solution, and it can be extended all the way to the boundary or to the border of that rectangle. So, shouldn't I actually draw something like that and be much, much happier with my result? And the answer is, well, it would be nice if it worked like that. But notice I said boundary or border, and I didn't say which one. So this more general version of the Picard theorem is actually typically ignored because it can also lead to this. You have your point, you have a solution, and it goes to this border and this border. It runs away to infinity. And this means that it really exists only on a small neighborhood. And you are back to where you started. This solution does not last long. It's just local, even though it extends to the borders of the rectangle. So from practical point of view, this more advanced version of the Picard theorem does not really bring more information. And that's why it's ignored by most authors. Okay, so that was the side remark. Now back to our example. This was the first stage, as I said, direct application of the Picard theorem. But now let's ask ourselves a key question. Okay, I have the plane here, and there are no restrictions. So potentially, there are solutions passing through every point. After all, the Peano theorem says so. Every point in R square is a host to a little local solution. So what are the points where I do not have uniqueness? Could it be this one? And the answer is not really, because m here was actually an arbitrary positive number. Let me put it here. M positive, arbitrary. So when somebody is interested in this particular point, I have no problem actually making m a little bit larger, and this strip gets wider and swallows up this point. And if somebody comes up with this point, I can again extend, make the strip wider. So the second stage of the Picard analysis is, and I put it in quotation marks because this is not really proper, but it's sort of like a limit process. I will send m to infinity. And when I send m to infinity, the strips get wider and wider and wider and swallows up essentially everything. Every single point of the plane gets swallowed up by those enlarging strips, which means that every single point in the plane gets the benefits of our Picard theorem. So stage 2 actually ends up with the following conclusion. Through every point in plane, there passes a unique, and I put it in brackets, local solution. And that's the conclusion that we want to see. It's a global conclusion. There are no m's in it anywhere. I just look at it and I have perfect information. Every point in the plane is a host to a solution which is unique. Wonderful, the best possible conclusion that you can have. Okay? So we are understandably happy about this conclusion, but we are actually even more happy than you appreciate right now. Let me show you that there is more to it. This example has been used in the lecture on separation, and we actually introduced those tricks with logarithms, absolute values, things like that, stationary solutions. This has been a key example in that lecture, but actually the solution was not quite complete. But I didn't talk about it because we were not ready. Now we are. Let's recall something. When we are solving this example, we first separated the case when y is equal to 1. And we got the stationary solution. And then we said, okay, if y is not 1, then we can divide by y minus 1, we can play the separation game, and we got a general solution. But we should have asked a key question. What if some solution actually does not fit in either category? There is a third category that we totally ignored, which wasn't, of course, proper. What if some solution starts away from 1, but connects to 1, like that? Such a solution does not fit into either category. So if there is such a solution, we totally missed out on it. We didn't know about it. So how could we talk about a general solution if we don't have some solutions included? That was a gap in our solution. Could it happen? And the answer is yes. In my lecture notes, there is a section on gluing solutions. This is actually fun, but it complicates life a lot. So I'm actually avoiding problems like that on a test because, yeah, they are tricky. But if you are careful, you should think about it for a second. Fortunately, and this is where we are getting to it, we have the Picard theorem and its conclusion. This second stage. And this second stage says it will never happen that two different solutions will meet. So the Picard analysis actually rules out this third case. And now finally, after all those lectures, we know that what we did in the first lecture was correct. There are just two cases which are separate. They can never merge. So it was correct after all. But we didn't know for sure. Now we know for sure, thanks to Picard. And that's essentially the happy end. It doesn't get better than that. I'm not going to ask for the Picard analysis on a test, but it's a nice topic for, let's say, more advanced students or students who like challenge. So in case you want to look at some problems in my lecture notes or in the practical practice problems, I'm going to show a few more examples to teach you two important tricks that you need to know in order to be able to handle all kinds of right-hand sides, because what we need is tricks for right-hand sides to make it bounded, okay? So this is a bonus. If you are not really interested, then okay, see you next time. Otherwise, stick with me and I will show you something interesting. Okay. There are two essential tricks for doing the Picard analysis, and we already encountered one of them, but that example was really too simple. So we revisit it again with a, let's say, more interesting example. By the way, this has been the first substantial differential equation that we encountered in this course. So we know that it does not bring any restriction with it. And therefore, our starting point is the whole R square, the plane. Okay, we need to take the right-hand side, treat it as a function of two variables, and find partial derivative by y, which is fairly simple. This is a product, x form, that's just a constant for now, and we differentiate the exponential. Here we go. So, the key question. Can we make this expression bounded by restricting our attention to a specific rectangle here in the plane? And the answer is, well, probably yes. What can go wrong? Well, x could go to infinity or to negative infinity. That would really make us mad. So we ban it. Okay, infinity, we just banned it. No infinity for x in our rectangle. Negative infinity. Okay, let's get rid of it. Here we go. Negative m, so it's symmetric. But again, we will see that it does not really restrict us in any way. Okay, let's have a look here. Exponential. What can happen there? Can e to negative y blow up? The answer is yes. But when? If y is infinity, then we get e to negative infinity, that's 0. That's nice. So infinity for y is no problem. We can leave it there. Negative infinity for y, when I substitute it here, I get e to infinity, which is infinity. I definitely do not want that. So negative infinity has to be cut away from my rectangle. And again, I could introduce a new letter here, but it's nice if I just put negative m over here. So m is positive. Let me put it here. Now the picture makes sense. Okay, so our rectangles now are enclosed from the right, left, and below from below, but they extend upwards without any restriction. And I claim that this is exactly the right type of rectangle I'm interested in. So, how does it look like? Negative mm, that's for x, cross negative m, infinity. That's my rectangle. And I claim that on this rectangle, the partial derivative is bounded. How do I prove it? Well, I just look at the restriction. The first restriction comes from this interval. It says that x is less than or equal m in absolute value. The second restriction comes from this. It's a restriction for y, and it says that y is greater than negative m. Actually, I should put strict inequality here, but I don't really care. I could easily put also inequality with equality in it, non-sharp inequality, because the Lipschitz property also has this type of inequality. So actually, I could use closed intervals. This is just a technical thing. I don't really have to worry about it too much, okay? So I have these two restrictions, and using these, I need to figure out that this expression is bounded. Well, this first condition helps me with the first part, And this second is supposed to help me with the second part. So let's have a look at it. Okay, I need to know something about negative y. So I multiply this inequality by -1. And it becomes minus y less than or equal to m. And now I apply exponential to each side. Exponential is an increasing function, so the inequality stays put, and I get e to m, e to -y. And moreover, exponential is always positive. And because it's a positive number which is bounded from above, I can pass to absolute value. And that's exactly what I wanted. So I have a bound on the first part in my partial derivative. I have a bound for the second part, and therefore I can put this all together, and I can claim that the partial derivative in absolute value is bounded by 2m e to m. And that's exactly the type of information I've been looking for, okay? So my partial derivative is really bounded, and therefore, by the Picard theorem, I have local existence and uniqueness. Where? Well, on rectangles like that. On all of them, for any positive m. So that was stage 1. Now we pass to stage 2. We start blowing up these rectangles by taking m larger and larger and larger all the way to infinity. So we can imagine how those rectangles are blowing up. Are there any points which are left out? And the answer is no. Every point in the plane, no matter where, gets eventually swallowed up. And this is, by the way, the reason why I can afford to use rectangles which are symmetric, because I'm blowing them up anyway. So there is no point in trying rectangles which are unbalanced. It wouldn't really help me at all in any way. It would just introduce more letters into my picture. Okay, so by blowing up, I reach the following conclusion. Through every point, in R square, there passes a unique solution. And that's the happy end. Here we go. That's the conclusion. So that was, let's say, type 1 example, type 1 differential equation, where I have to bound or I have to worry about infinities. Okay? And you can imagine easily many more expressions that force you to cut away infinities, perhaps all 4 of them, or just few of them, depending how the expression looks like. So that was the first trick, cutting away infinities. Let's have a look at the second one. So the differential equation now goes like this. Y prime is equal to x. That's a nice differential equation, perhaps, but it's not explicit because the derivative is not isolated. So we can expect trouble, by the way, sometimes. This looks like an interesting differential equation, let me put it this way. But on the surface, when I look at it, I do not see any restrictions. So potentially, I can expect solutions everywhere. That's a good start. However, for the analysis, I have to isolate the derivative. Here we go. And now we have to start asking questions. So, step 1. What is the partial derivative of the right-hand side with respect to y? And again, x is a constant, so we can pull it out. And I take the derivative of y to -1, or if you are experienced differentiator, you can do it like that, and you remember how it goes. So that's the partial derivative, minus x over y squared. Okay, what can go wrong? Well, first of all, we see the familiar trouble with x. X could blow up if we allow infinity in, or if we allow minus infinity in. So let's cut them off. Okay, here we go. We have a nice infinite strip, and this takes care of the x part. What can go wrong with y? Well, infinity I don't mind, but I worry a lot about 0. When y gets close to 0, this ratio gets really huge. So I have to prevent y from going arbitrarily close to 0. And that's the second trick that we know, preventing variables from getting close to a specific number. And the trick goes like that. I choose a safety corridor, sanitation corridor if you want, quarantine, of a specific width. Now, I could use m here, but actually, you will see in a second, I would have to use 1 over m here for this distance. So it's more convenient to introduce a new letter, although I don't really enjoy doing that usually, but here it makes sense. So m is positive, and epsilon is also positive. Two positive numbers, and epsilon, it's traditional in analysis that it's supposed to be small, and even smaller and smaller and smaller, okay? You will see. So by introducing two positive bounds, one cuts away infinity for x, and the other one cuts away 0 for y, I'm actually obtaining two different rectangles. One rectangle is here on the top, and one is here on the bottom. So, on negative mm cross negative infinity negative epsilon, negative epsilon is the upper bound for the lower rectangle, and on negative m cross epsilon infinity, that's the upper rectangle, I claim that the partial derivative is bounded. How do we get there? I'm optimistic here. Well, let's see. From this part, we have a restriction on x. That's a familiar restriction, no problem there. So, partial derivative by y, an absolute value, is bounded over here by m on the top. How about the denominator part? There is actually a way to describe restriction for both of these rectangles at the same time. I could handle each of them separately, because this restriction says that y is greater than epsilon. And this restriction says that y is less than negative epsilon. But I can write it in a common way like this. Y is greater than epsilon. Y an absolute value. Yes? That's a common way to describe these two restrictions. And again, I could put equality here if I want, just because I like it. Okay, now if y is greater than or equal to epsilon, then y square is greater than or equal epsilon square. These are two positive numbers, so if I square them, the inequality is preserved. One has to be a little bit, careful when squaring an inequality. But with two positive sides, this is okay. And now I just do the division, and I learn that 1 over y square is less than or equal 1 over epsilon square. And that's exactly the inequality that I need for handling 1 over y square. So I put here epsilon square, and I am ready to reach my conclusion. The partial derivative is bounded. So this is the second trick for getting rid of a specific number, and it works nicely through some epsilon. And now I can call on Picard. If the partial derivative is bounded on these two rectangles, then we have existence and uniqueness on those two rectangles. Let's make a conclusion. A global conclusion, stage 2. Okay, what do we do now? We send m to infinity, and we send epsilon to 0 from the right. So we are extending those rectangles outwards in the horizontal direction, and at the same time we are moving them closer and closer to the x-axis. Are there any points that we are not going to reach, that are not swallowed up by this process? Notice that epsilon is always positive, so there's always some separation. And as we are moving in, we will never get to the x-axis. The points on the x-axis, they are not reached at all. How about the remaining points? Well, it doesn't really matter how far to the right or to the left they are, because you can always increase m. So this is okay, this point is okay, this point is okay, you just increase it. How about if you take a point which is really close to the x-axis? Really, really close. Well, if it's close, it means there is a positive distance. Yeah? Either it is on the x-axis, and then we know it's out, or it's away, and then there must be a positive distance. And when there is a positive distance, you can always take half of it as your epsilon, and the rectangle moves so close to the x-axis that it follows up this little guy. And if you take something which is even closer, again, you take epsilon smaller. So you can get arbitrarily close to the x-axis and follow up everything with the exception of the x-axis. So through all points, now how to write it? With y not equal to 0, there passes a unique solution. Perhaps, if you don't like it like that, you could try some alternative. Let me just make a little sidestep here. You could, for instance, form a set. Through all points from the set R square minus x0, x belonging to real numbers. That's one alternative, okay? You take the whole plane and you subtract the x-axis. And you get the remaining set. This is the minus sign, set minus. And you can just call on it. Yeah, there are many ways one can express this conclusion. But the bottom line is, as long as you stay away from the x-axis, there will be nice unique solutions. And what's happening on the x-axis, we do not know. There could be solutions, or perhaps not, or perhaps there are multiple solutions. It could be that there are solutions crossing or merging, things like that. So this is actually a very interesting situation. When you finish your Picard analysis, and you do not get existence and uniqueness everywhere, this is actually not a bad news, because it means that things are getting really interesting. They are not boring anymore. Yeah, this is boring. I mean, okay, that's nice, but boring. And this is really interesting. What is happening here? I want to know. I could spend another blackboard on it. But we are here talking about the Picard theorem. So, okay, let's leave it with a heavy heart. Okay, we just learned the basic two tricks, and that's it. So let me just quickly go through, I don't know, 2 more examples just to show something. Okay, here we go. Y prime is equal to y over 1 minus y. That's a nice differential equation. Could be from some application, because there is no x in it. Okay, so we had a special category for these equations. And we also see the first restriction. Y must be different from 1. So when I'm drawing the basic picture, on level 1, there is a gap. That's the basic situation. Okay, partial derivative. Well, partial derivative. Do I feel like it? Not really. Because I will have to use the ratio rule, or the fraction rule, whatever you call it, the quotient rule, which is a lot of work. Can I avoid the work? The answer is yes, I can. I can avoid the work if I subtract 1 and add 1 virtually on the top. Virtual reality, very, very modern today. So let's try it. Minus 1 here, plus 1 here. Y minus 1 divided by 1 minus y is simply negative 1. And then I divide here, and I get 1 over 1 minus y. That's an alternative way to express my differential equation, the right-hand side. And then when I take the derivative by y, this is actually fairly simple, because here I differentiate and I get 0. That's easy. And here I just use the chain rule. It's 1 over 1 minus y squared. That's the partial derivative. Okay, so I want boundedness. So what do I have to cut away? Well, I'm actually not cutting away anything for x, because x doesn't feature here at all. I'm not cutting away infinity for y, because it doesn't bother me at all as well. The only thing which bothers me is number 1 for y. If y is close to 1, then I'm, 1 over 0 is infinity. That's really bad. So I need to cut away the value 1 from all the points, which means I'm cutting away horizontal strip again, and I introduce a certain width. actually I can think of this as a strip around the value 1. So I will extend it like that, and I will introduce here little epsilon as the width of the strip. And I get two rectangles which go like that. What kind of rectangles do I see? Okay, here. For x, there is no restriction. And for y, I can go upwards, which is I start from 1 plus epsilon and go to infinity. Or the second type of a rectangle, I start at negative infinity and go upwards until I hit 1 minus epsilon. So that's the two types of rectangles that I have. And once I have them in place, I can do a little analysis which uses the fact that 1 minus y is definitely more than epsilon. And you play with this in a similar way that I did over here, and you get a nice upper bound for the partial derivative. Okay? So that would be the Picard stage, the first stage, identifying rectangles and showing boundedness of the partial derivative. So that would be the Picard. And then we send epsilon to 0, and we can see that we have existence and uniqueness for points xy with y different from 1. Because when we send epsilon to 0, these two rectangles, they almost merge, but there will be a gap between them. Gap which has width of one line, which is 0. Okay? Well, actually, that's another way to express our conclusion, that we have existence and uniqueness for specific points. Okay? So this is really just a modification of the previous example, but here the number that we wanted to avoid was 0, and this is just to show you that we can avoid any number. We are just careful writing it down. Okay, no problem there. Of course, you may say, okay, how about this example that we had in the previous lecture? Y prime is equal to y over y minus x. Good question. Well, again, I just imagine here virtual minus x plus x on the top, and I get 1 plus x over y minus x. That's the right-hand side. And the partial derivative, therefore, is, and that's my last chalk, so it seems that the lecture is almost over. Okay, I take derivative here. X, of course, x stays on the top as a constant, and there will be y minus x squared and minus here. Minus, not a continuation of the fraction line. Minus. Okay. I hope it's obvious. Okay. That's my partial derivative, and of course we saw it in the previous lecture. There is the main diagonal, which is forbidden. And now we can see that when we get close to the main diagonal, we also have trouble with our partial derivative. So if you want to go for boundedness, we have to, first of all, get rid of infinity in the numerator. I don't really like it there, but it's life. Okay, there is some constant m over here, and let's say negative m over here. But then we have to prevent the points x and y from getting too close to the diagonal. In other words, we have to prevent x and y from being almost the same. So we have to introduce some safety strip around the diagonal. But when you introduce a safety strip around the diagonal, you no longer get rectangles. You get triangles, so to speak, or trapezoids, or whatever. This is really, really complicated, as you can see, compared to the previous examples. So one has to be careful. We have to introduce rectangles that essentially go like that, but we do not want them to go all the way to the diagonal. Now we need obviously another constant over here, let's say L, and let's just make sure that we know that m is positive because we are cutting away infinities, but L can be any number, and when I'm looking at it, okay, it makes sense if it's between negative and m. It could be negative, because this rectangle could also be here. Okay, and it could also be here, by the way. Another L here. So L, and this one has L here. L can be anything between negative m and m. So now we have actually like a thin strip, and we have to cut it away so that it's below the diagonal or above the diagonal. Now, this is the diagonal. So if this position is L, then also this position is L. If I use L also for the y coordinate, then this corner will be exactly on the diagonal. It's actually an open rectangle, so it does not include the diagonal, but it gets arbitrarily close. And this would lead to trouble over here. So I have to introduce a third constant, which will take this corner and shift it. And I can shift it downwards or to the right for this type of rectangles. And it's up to me. So let's say that I'm going to shift the y coordinate a little bit downwards. So those rectangles which are below the diagonal, they should look like this. They go from L to M. So I'm in the strip. And the y coordinate can be anything downwards. And upwards, I want to let it go all the way to L, but not quite. I stop it short. And this creates vertical displacement whose size is epsilon, and that's the rectangle that I have. Like that, infinite rectangle. It does not reach infinity on the right nor on the left, so the numerator is safe. And it has a specific distance from the diagonal, which is not quite epsilon. The distance is measured like that, in an oblique way. But this distance is definitely positive. You can calculate what it is. Something like epsilon divided by square root of 2 or whatever. Yeah. OK, that's one type of rectangles. Now for the upper guys. So I am now aiming for this guy. OK. This rectangle starts at negative m, goes all the way to L for x, for the x variable. And for the y variable, it can go up any way it wants. And the lower cutoff point is L plus epsilon. Because L is on the diagonal, and I want to move it a little bit up by epsilon. OK, that should be it. And now showing that the derivative is bounded takes a little bit more work, but this is the basic idea how we deal with complicated situations. And you can easily imagine that I may be in a situation when, let's say, there is a circle which I don't really like, and I want to avoid it. So I have to start taking rectangles inside a circle and outside of the circle. Things can get really, really complicated with the Picard analysis. Okay? Fortunately, cases like that are not all that often. All that frequent. Typically, you have something like that, or perhaps something like that, and now we know how to avoid oblique lines. So if you really like challenge, you can look at some more advanced examples for the Picard analysis, but this is really quite good already. Okay? So if you can handle these simpler cases, you are still good. And that's it for the bonus. So I hope it was worthwhile for you, and see you with the next video.